Hi everyone. In this talk, I will present our CHI 2020 paper, How Relevant is Hicks Law for HCI? I'd like to start by asking the question, what is Hicks Law and how did you understand it? If you can, please write down some keywords and see if this talk changes your mind. Hicks Law was first introduced to HCI in the early 80s as uncertainty principle. It describes quantitatively the time a person takes to make a decision among a set of n choices. Here H is the information theoretic notion of entropy, and H varies depending on the probability distribution of the n choices. While Hicks law, or rather the choice reaction paradigm, is a classic topic in psychology, it has an interesting position in the HCI community. The law is ignored in many HCI textbooks, but it is taught in HCI classes as one of the few quantitative laws. We interviewed a few HCI professors and received replies such as, it is about response time, decision-making time. I have 2 slides about the law adapted from the slides by someone else, and I teach it, but I don't feel 100% comfortable talking about it. Conceptually, it is often regarded as a fundamental law of interface design. One can find numerous online articles and design books discussing how understanding Hicks law can improve interface design. Because time is a logarithmic function of the number of options, the Hick-based design principle advocates the concept fewer is better. In practice, the law has not seen many successful applications. We surveyed some HCI studies that used Hicks law and find that it has been applied in visual search, decision, mode switch, etc. Some of them find the law applicable and some don't. So where does the law apply? In this article, we'd like to dispel some misunderstandings about Hicks law and provide a clearer picture of the choice reaction paradigm. We want to answer the following questions. What exactly is Hicks law, and how relevant is it for HCI? First, we revisit the historical context of the choice reaction paradigm in psychology, since it has a long history. The first results on reaction time have been reported in 1850 by Helmholtz. Then Donders introduced the 3 types of reaction time, where choice reaction time is the longest, following a given stimulus-response mapping rule. Michel showed for the first time there might be a relationship between time and the number of stimuli. Then Blank mentioned the logarithmic relationship without giving further explanation. Then information theory was introduced, and Hick and Hyman's work came to our attention. There's much more information here, please refer to the paper. Hick used the information theoretic rationale that was popular at the time to interpret the logarithmic curve. He considered the human as a channel of information transmission, therefore reaction time is seen as resulting from the uncertainty of the stimulus. In his experiment, 10 lamps were arranged in an irregular circle and connected to a device that was coded to light up a random lamp every 5 seconds. Each of the participants' fingers was connected to a key, and the relationship between the keys and lamps was predetermined. The participant's task was to press the key corresponding to the lamp that lit up. Hick trained the participants 8,000 trials before the real experiment and find that the time one takes to press the key is proportional to the entropy of stimuli. Hyman changed the distribution of stimuli from uniform to non-uniform and performed an experiment where participants react vocally to a visual stimulus. Similar to Hick's experiment, Hyman predetermined the relationship between stimulus and response and trained participants for more than 15,000 trials. He also found that the time is proportional to the stimulus entropy. A lot of studies have been conducted in psychology to study the stimulus response paradigm. In summary, most studies were conducted on very simple tasks, such as responding to bulbs lighting up by pressing keys or through speech. Generally, the stimulus entropy is between 1 and 4 bits, meaning less than 16 options. And perhaps most importantly, the effects of stimulus-response compatibility. Stimulus-response compatibility characterizes the fact that it is easier to respond to a stimulus using certain responses than others. For example, if the stimulus is coded in digits, it is easier for someone to call out the corresponding digit than to call a letter. And this is similar to direct and indirect mapping. For example, the design of knob to burner on the left is more direct and easier to understand than the one on the right. While Hick and Hyman find the effect of the stimulus entropy on time, many other psychologists did not due to the high stimulus-response compatibility. For instance, in Mowbray's experiment, participants reacted to the visual presentation of Arabic numerals by merely reading them aloud. There is virtually no effect of stimulus entropy. The last but not the least results are related to learning. If participants are heavily trained, the effect of stimulus entropy can be worn out. For example, in another experiment, Mowbray showed that reaction time for choices among up to 10 possibilities could be reduced to that of 2 choices when a subject practiced the key press task for a period of 6 months. It is clear that, at this point, Hicks Law is much more complicated than usually reported in HCI. As I said earlier, there are much more details in the paper. Based on our revisit of the historical context of the choice reaction paradigm in psychology, we propose a more comprehensive version of Hicks Law. Choice reaction time for simple tasks grows linearly with entropy in the range of 1 to 4 bits. The higher the stimulus-response compatibility, the heavier the training, the shallower the slope. With the appropriate training, the effects of stimulus-response compatibility and stimulus uncertainty can be reduced to almost 0. Now let's look at the HCI experiments that have used Hicks Law. If we compare them with the choice reaction paradigm in psychology, we could argue that Hicks Law has often been misused in HCI, and in fact it is largely irrelevant to HCI tasks. The first confusion is the notion of reaction time. As we presented earlier, the reaction time studied in psychology is choice reaction time, where response follows a certain stimulus-response mapping rule that requires learning. However, this notion has often been misunderstood and misused in HCI to interpret the time one takes to react to anything, as we've seen from literature. All of these processes happen during what we call response latency, the time one takes to complete a sequence of covered, unobservable mental processes, and some of them can indeed be explained by a logarithmic function of the number of stimuli, but attributing them to Hicks Law is a very unfortunate conflation between the formula and the law. The second confusion is the stimulus-response compatibility. As we've seen previously, the slope in Hicks Law depends on stimulus-response compatibility. Different from psychology studies where the stimulus-response relationship is manipulated, every HCI task has an extremely good stimulus-response compatibility. We always ask participants to respond to the exact corresponding stimulus, such as selecting item 4 on the menu when item 4 is lit up. We rarely ask participants to select item 10 when 4 is lit up or type a letter. Therefore, we can expect a very shallow slope of Hicks Law in HCI studies. We demonstrate this using data from 2 previous studies and show that, in practice, the psychology of choice reaction time can usually be treated as a constant. The third confusion has to do with the notion of learning. In HCI studies, an important issue is whether Hicks Law applies to novice users, expert users, or both. Again, here we believe that it depends on the task, stimulus-response compatibility, and practice. In HCI studies, the learning effect often comes from a new interaction technique and task, but does not come from the mapping between stimulus and response due to the extremely good stimulus-response compatibility. Therefore, all users can be considered as experts in the choice reaction paradigm. Comparing the historical context of the choice reaction paradigm and the use of Hicks Law in HCI studies, we show that many phenomena can be characterized by a logarithmic function of the number of stimuli, but cannot be explained by Hicks Law, and the psychology of choice reaction time can be assumed to be constant. Now let's further examine the use of Hicks Law, or rather a logarithmic function in design to justify the need to display as few items as possible. Unlike controlled experiments where the stimulus is explicit, in this scenario, the stimulus is inexplicitly defined by the user's goal of selecting one item among a set, which involves more than just the simple choice reaction in the response latency process. Imagine a designer has to display all 32 items on some website, and we assume that response latency can be predicted by Hicks Law or a logarithmic function. The first option is to display all of them on the same page. This gives us a plus 5b amount of time. The second option is to split the 32 items on 4 pages according to their colors. In this case, the person chooses a category first, then an item within that category, and this gives us 2a plus 5b amount of response latency time. The third option is to split them randomly on 4 pages. The person choosing the item will not always find the item on the first page. On average, she needs to go through 2.5 pages before finding the right one. Here, response latency is 2.5a plus 7.5b. So in fact, the optimal strategy according to Hicks Law or a logarithmic function is to display all items at once on the same page, which contradicts the Hicks-based design principle. Therefore, these design principles cannot be justified by Hicks Law, nor any other logarithmic response latency function. There are many different phenomena taking place when the user is investigating the items, which are far more complex than simple stimulus response. Despite the complexity of the psychological process behind response latency and the many potential response latency functions, we propose 2 design principles based on whether the response latency function is convex or concave. The first design principle is that if items are not categorized and the response latency function is convex, then grouping them will reduce response latency. And if the function is concave, then it is better to display all items at once. And if items are categorized, then they should always be split. Please refer to the paper for more details and mathematical proofs. To summarize, we show that Hicks Law is often misused in HCI, and the psychology of choice reaction time is of little relevance to most HCI applications because high stimulus response compatibility and over-learned tasks result in almost constant choice reaction times. Logarithmic growth of observed temporal data is not necessarily interpretable in terms of Hicks Law. Many mechanisms can lead to a logarithmic function, such as visual search in a hierarchical menu or scrolling on an alphabetically organized menu. These cases have nothing to do with the choice reaction paradigm. Using a simple car scenario, we also demonstrate that Hicks Law, or rather a logarithmic function, cannot justify the Hicks-based design principle for organizing a set of choices. For user interface design, a detailed examination of the cognitive processes involved in response latency, such as visual search and decision-making, is more fruitful than a mere reference to Hicks Law. We plan to create an empirical taxonomy for response latency, which might be useful for HCI researchers who strive to model human behavior. And thank you for watching.